Now, in conclusion, we will then say that an arithmetic sequence is a sequence with the following properties. One would say that it has a common difference. And this common difference is defined as D, because the number that we said it's D, we're adding D, right? But in this case, it will be defined by Tn plus 1 minus Tn. We spent a share amount of time in lesson 1 looking at the fundamentals of sequences and series. In this lesson, we are going to use the basics we learned in lesson 1 to study a specific sequence called arithmetic sequence. To understand this sequence, let's say we build a sequence starting with term 1. And suppose we call that term 1 A. So we give it a number A. The A in this case would represent any number. It could be a 2, it could be a -1, it could be 100. It's really any number. I'm just taking the variable A to represent the first term, T1. With an arithmetic sequence, if I want to go to the next term, term 2, what we do is that we add some number D so that we are able to go to the next term. This would mean that I will have the A plus the D, and that will define the next term to be A plus D. If I continue doing the same thing to get term 3, I will add the D again. So D again is an arbitrary number that I choose. It's any number as well. So if I add here, I'm going to have the A plus D, which is this here, and then I'm adding a D to it. So this is going to be plus D. This would give me the D plus D to be a 2D. So that means I'm going to have A plus 2D. And this whole thing now will then be my term 3. That means I'm going to have A plus 2D. I can continue doing the same thing by adding some number D so that I get now the next term that comes after this. It should be clear to you that I'm going to take the A plus 2D, the previous term that I just got, and I'm adding a D to it. So we add a D here. So that now I'm going to have the A plus a 3D, because these two will give me a 3D. And this will then mean that the next term would be A plus 3D, and that is term 4. To extend the sequence, I can continue doing the same thing by adding the same number D to get the next term. Now, there's something very interesting to observe in this sequence. We see a pattern here that when we look at term 1, we have the number A. If we go to term 2, we have the number A. If we go to term 3, we still have the number A. And term 4, we have the number A. If we continue with this pattern, we can see that we'll still have A in term 5 and A in term 6. So A seems to be some constant number that is always showing up in this sequence. The other thing is that when you look at term 1, we actually do not have a D here. It's just an A alone. However, when you look at term 2, we see a D here. When we look at term 3, we see a 2D When we look at term 4, we see a 3D. There's some pattern going on here. To study this pattern, I'm going to look at it from a different perspective. Say I rewrite these terms here at the bottom as to say I have an A plus 1 minus 1 times a D. This would give me an A plus a 0 times a D. Now, if you look at this is the first term here, because I can see that I'm always having one less than number of terms here. So this means that if I say the first term minus 1, the 1 here, the first term, and then I subtract the 1 from it, I get a 0. And a 0 times a D, it actually gives me the A, because this whole thing will reduce to an A. If we look at the second term, I can rewrite this as A plus 2D minus 2 minus 1 times a D, because I can see that this would simplify into an A plus 1 times D, because remember a 2 minus 1 is just a 1. But when you look at this, it actually gives me the second term, A plus D. I get the A plus the D, because the 1 times a D is just a D. If we continue doing the same thing here, you can see that I'm going to have an A plus, because we are on term 3, I'm going to say 3 minus 1 times a D. And this would then reduce to A plus a 2D, because here I'm going to get a 2, and a 2 times that is a 2D. And that's exactly what we have in term 3. And the same thing will be true with term 4, because we can simply say 4 minus 1. It will give us the 3 times the D. And the A, we said, is always like that. You can see even here, it's always appearing as a constant number. It doesn't change. It doesn't multiply any number. So we are noticing a pattern here between the number of terms and the number that appears on the D. The number that is on the D is always 1 less the number of terms. 1 less the number of terms. 1 less the number of terms. Hence, I'm saying even here, I'm going to say 1 less, the 4 minus 1, then I should get a 3, which is 1 less the number of terms. It's like the number of terms minus 1. Then you get the combination of the D that appears in each term here. Of course, in the first term, it doesn't appear because it reduces down to a 0. That's the unique pattern that we see in an arithmetic sequence. I can continue this sequence such that here I have T5, let's say, for instance. This means that here, if I were to write this term, I will say it's an A plus 1 less the number of terms, 5 minus 1, and that will actually give me a 4D. It's a pattern that an arithmetic sequence displays all the time. We know from the previous lesson that if we continue doing a sequence like this, there is a point where we get to the nth term, what we call Tn. This term here, if we use the pattern that we have observed in this sequence, we can see that we'll end up having an A because it's always appearing there, but we're going to have a plus 1 less the number of terms. That means we're going to say n minus a 1. We're going to have an n minus a 1, and we always multiply this by a D. And this would continue like that if it continues any further. So in this case, we're saying the nth term of an arithmetic sequence is defined by A plus n minus 1 times D. So this proposes an equation or a formula for an arithmetic sequence, because then we can use this to find any of these terms or even the ones that come after this nth term of an arithmetic sequence. Now, what am I saying? I'm saying here that term 1 of an arithmetic sequence is defined by A. Term 2 would be A plus D, because we need to have 1 less the number of terms there on a D. Term 3 is going to be A plus 2D. And this can continue like that until maybe we get to some term 5, the fifth term, which is going to be A plus a 4D. Because always here we have 1 less than number of terms. We're subtracting 1 from the 5, we get a 4D. The pattern would be true even if I take, let's say, term 11, because I'm still going to have an A plus 1 less the number of terms here is going to be 11 minus 1, which is a 10D. And if we continue doing like that, we can then represent the nth term as a formula to say the nth term, because remember in lesson 1 we defined Tn as the nth term. So we can say the nth term is going to be given by A, because we know that our A doesn't change, it always appears as it is. But here we're adding 1 less the number of terms. The number of terms minus 1 less the number of terms, and we multiply by a D. That's a pattern we have observed in an arithmetic sequence. Now this then serves as a general formula. It actually says to us here that the nth term of an arithmetic sequence is equal to the general formula. So if you want to define an nth term of an arithmetic sequence is given by this formula, A plus n minus 1 times D. For example, this formula actually helps us to find any of the terms. So for instance, if let's say I was looking for term 1, let's say T1, I would use the formula so that I now have the A as it is, and I'm going to substitute the 1 here because I'm looking at term 1, so that now I have 1 minus 1 times D, and this will reduce down to an A, because here I'm going to have a 0, the whole thing will disappear, and then I have A. You can do the same thing with term 2. That means I'm going to have an A, which is this, and I'm going to put a 2 here because I'm looking at term 2, so that now I have a 2 minus 1 times D, and this says to me I have A. Here I'm going to have a 1 times D is just going to be a D, and term 2 is going to be defined by A plus D. Now if you are paying attention, you have to see that I'm reproducing these terms using the general formula. That's why we say this is a formula. It helps us to find any term in the sequence. Remember, we said the nth term represents any term in the sequence. And you can do this pretty much with every term, any term that you like. I can take the 11th term just to check our theory. This would be A plus 11 minus 1 times D. And this should reduce down to A plus 11 minus 1 should be a 10D. And that's exactly what we have found. You can do it with the 50th term, the 100th term, and so on. There's a very unique thing that we have to also observe with the arithmetic sequence. We are saying here that it is defined by Tn is equals to A plus n minus 1 times D. Sometimes this sequence is called a linear sequence or linear number pattern. The reason being is because it has the form y is equals to mx plus c. The c here is actually the same as the a because it's a constant, it's a number that doesn't change. We have seen it here when we studied our sequence that the a doesn't change, it's always the same. If you were to look at it from the standard formula of a linear equation, you would see that it's a constant that doesn't change, it's a c. And our gradient, the m, actually is given by n minus 1. So these two are also the same as well. And of course, the x in this case would be represented by the d. Because it has the same structure as the linear equation. We sometimes call this a linear sequence or linear number pattern. So say for example we are given a sequence that starts with a number 2. We are saying here that to get to the next term, I can add, let's say, 2 would represent the A here, right? Is the first term. I can add, let's say, any number. Let's say I choose to add 2 here. Now I'm going to have a 2 plus a 2, and this will give me a 4. If I add the same number that I added at the start, like a 2 here, I then now have a 4 plus a 2, and this actually should give me a 6. I can continue adding the same number again, so that now I have a 6 plus a 2, and that gives me an 8. And this pattern will continue just like that by adding the same number 2. That's essentially what we're saying here if I were to represent it with numbers, because I've done it with symbols at the top so that we understand where this formula comes from and what are the dynamics of an arithmetic sequence. Say, for example, we are given an arithmetic sequence such that we have T1 defined by A, of course, and we have T2 which is going to be defined by A plus D, and we have T3 which is defined by A plus 2D. And this continues going on like that because it's an arithmetic sequence. If I were to say here that term 2 minus term 1, I will actually have the A plus D, which is term 2, A plus D, and I'm going to subtract the A from it, which is term 1. This is term 1 here, so I'm going to have negative A. And this will reduce down to the A and the A would cancel each other out because A minus A is a 0. So these two will cancel each other out so that I have a D. If I were to take term 3 minus term 2, this would give me term 3 is going to be A plus 2D. And I'm going to subtract term 2, which is A plus D. So here I'm going to have minus open bracket A plus 2. Remember, I have a binomial here. That's why I have to put the brackets when I'm subtracting. Now, this will reduce down to A plus 2D minus A minus a D. So that we can see that the A minus A is going to cancel out again, giving us a 0. But now I have a 2D minus a D. That should reduce down to a D. If you have 2D minus a D, it will simply give you a D. You have to notice that when I take this, subtract that, I get a D. And when I take this and subtract it from that, I get a D as well. I get a constant number. And this is not a surprise, actually, because we said that to build this sequence, we're adding the same number D. It means if I subtract these terms, the succeeding terms, I should get that D as well. So that's another way actually of finding the D. You subtract the previous term from the next term. So here what we're saying we can see that we have a common number. But this number is not just any number, it's a difference, meaning a number that we get after we have conducted subtraction. We then call this a common difference because difference means a number that we get after subtraction. So this D here is not just common, but it's also a difference. And the same is true if we were to look at our example here using numbers. If I say term 2 minus term 1 is going to be 4 minus 2 is going to give me a 2. If I say term 3 minus term 2, I'm going to have a 6 minus a 4, and that will give me a 2. If I say term 4 minus term 3, I'm going to have an 8 minus a 2, and that should give me a 2. That's how you'll find the difference between these two successive terms. And we call that a common difference because it's a common number. It is always the same. Now, in conclusion, we will then say that an arithmetic sequence is a sequence with the following properties. One would say that it has a common difference. And this common difference is defined as D because it's the number that we said it's D. We're adding D, right? But in this case, it will be defined by Tn plus 1 minus Tn. What am I saying here? I'm saying that the common difference is defined by the next term minus the previous term. Remember that in lesson 1, we explained in depth what Tn means, what Tn plus 1 means, and what Tn means. This here is the next term, and this is the previous term. So if you subtract the next term, the next term from the previous term, you then get the D. If you subtract this from that, you get the D. So for instance, let's say that just to explain this formula further, if we say n is equals to 1, it then means here I'm going to have a D is equals to T, then I'm saying n here is a 1, so that means I'm going to have a 1 plus a 1, and then I'm going to have minus, and then here I'm going to have a 1 because we're saying n is equals to a 1. This will simplify to term 2 minus term 1. Do you see that I'm saying the next term minus the previous term, right? So this means that's how we're going to define the D. You can take it with a different number of n. Let's say you use n to be 2 there. You're going to have a 2 plus 1 is going to be 3. Then here we're going to have a 2. So T3 minus T2 is the next term minus the previous term. So this is a general way of writing it using the definition that we spoke about in lesson 1 for the next term and the previous term. The other property of an arithmetic sequence is that it has the nth term, or what we call the general formula, because the nth term and the general formula are actually the same thing as we have explained. That is given by Tn is equals to A plus n minus 1 times a D. And remember, this formula assists us to define or to find any term in the sequence. This lesson will expand now into practicing questions so that we can now use this equation or the formula of an arithmetic sequence and study different behaviors of arithmetic sequence.